Hello students. This PPT explains the second question given in the handwritten note. So the first question were about how to check the adequacy of a given design of the slender column. And this particular question is dealing with the design of a slender column for the given data. So the question is, an unbraced column 300 mm by 400 mm in section is unbraced in both the principal direction. The column ends are fixed and the column has an unsupported length of 3.9 meters. The column carries an ultimate axial load of 800 kN and ultimate moment of 80 kN and 40 kN about the major axis, bisecting the depth at its ends, assuming M20 grade concrete and Fe415 grade steel and effective cover of 60 mm determine the area of longitudinal reinforcement. So in this question it is clearly mentioned the column is unbraced, so it may undergo lateral drift or sway will be present. And its dimension is 300 mm by 400 mm, so the cross section is rectangular section and it is unbraced in both the principal direction, that is in about x axis and y axis it is unbraced, that is sway or lateral drift is may possible in both x and y direction. And the support conditions are given as, why the support condition is mentioned? To get, as discussed in the previous problem, we need to identify the L effective length of the column to calculate slenderness ratio. For that, the column N conditions are mentioned. In this particular question, the N conditions are fixed conditions and its unsupported length is 3.9 meters. And also it is given the column carries an ultimate axial load of 800 kilonewton. So since it is ultimate axial load, it is notated as PU. PU is given as 800 kilonewton and ultimate moment of 80 kilonewton meter and 40 kilonewton meter. So this is the external moment acting on that column. So two values are given, 80 kilonewton meter and 40 kilonewton meter. It is clearly mentioned this is acting about the major axis. So usually the major axis is taken as xx, which is bisecting the depth. So the major axis is x, bisecting the depth at its ends. So these are the moments which is available at the ends. So the column is having both top and bottom end. So these moments may be acting at 80 kilonewton meter, may be acting at the top, and 40 kilonewton meter may be acting at the bottom. So the materials are M20 grade concrete and Fe415 grade steel, and the effective cover is 60 mm. That is, D dash is taken as 60 mm, and it is asked to calculate the area of steel, area of longitudinal reinforcement for this particular case. So moving on to the first step, as usual our first step is given data. So in the question, the unsupported length is given 3.9 meters. It is notated as small letter L. This column is a rectangular column. So the dimensions B is 300 mm and D is 400 mm. The effective cover is given as 60 mm. That is, D dash is equal to 60 mm. The axial load, the ultimate axial load is given as 800 kilonewton, which indicates PU is equal to 800 kilonewton. And the two values of ultimate moment, external ultimate moment is given 80 and 40 as I told earlier. This may be acting at the two ends of the column, top and bottom end of the column. So, and also it is mentioned both are acting at about the major axis. So major axis is x axis. So I am going to notate 80 kilonewton meter as MUX1 and MUX2 is equal to 40 kilonewton meter is taken as MUX1 and 80 kilonewton meter is taken as MUX2. So let 1 and 2 be the two ends of the column, top end and bottom end. So 40 is acting at the top and 80 is acting at the bottom. And our main aim is, for the slender column we need to calculate, as discussed in the previous problem, we need to calculate both initial moment MUI and additional moment MA. So the total design moment will be sum of these two, MUI plus MA. So first we are going to calculate MUI. For that, as an initial step, I need to check the slenderness of this particular column. So for that, I'm going to calculate the effective length of the column. So effective length is calculated based on IS 456-2000, table 28, page 94. In that table, different support conditions are mentioned, and according to our question, we will choose one. So in our question, the end conditions are given as fixed. Okay, so fixed means, in general case, fixed means it is the lateral movement or a movement in x direction, y direction, and the rotation is restrained. But in this particular column, the ends are fixed, and also it is unraised. So unraised means the lateral drift or sway is allowable, or sway may occur. So while considering all these conditions, the perfect choice is this particular case. Okay, that is, the column is effectively held in position. That is, it may not move in x or y direction and restrained against rotation at one end, and other end restrained against rotation but not held in position. So that means this is indicating the sway. Okay, relative vertical movement of this column. So our choice is this particular case. So according to this 456 table 28 page 94, this case is showing that we have to take L effective is equal to 1.2 L. Okay, so since the column is unraised, considering lateral sway, L effective is taken as 1.2 L, where L is given in the question, which is equal to 3.9 meters. So L effective is equal to 4.68 meters. So next I am going to calculate the slenderness ratio. Slenderness ratio, since it is a rectangular column, I need to check the slenderness both in x-axis and y-axis. So in x-axis, the slenderness will be given by L effective by D. Okay, D indicates the dimension which is perpendicular to x-axis. So L effective by D, which is obtained as 11.7, which is less than 12. So the column is considered as short for bending about x-axis. But while considering the slenderness in y-y axis, so while calculating the slenderness in y-y axis, this denominator should be the dimension which is perpendicular to y-y axis. So the dimension is breadth, so L slenderness equation becomes L effective by B, which is obtained as 15.6, which is greater than 12. So column is long for bending about y-y axis. So for this particular case, this column is acting as short while considering the bending about x-axis, but it is slender while considering the bending in y-y axis. Next, I am going to calculate the eccentricity. Okay, so eccentricity is calculated using this equation, L by 500 plus D by 30. Here also, this D is the dimension which is perpendicular to the axis which are considered. Okay, so while calculating Ex minimum, this equation will be L by 500 plus D by 30, and while calculating Ey minimum, the equation will be L by 500 plus B by 30. So by using this equation, Ex minimum is obtained as 21.13 and Ey minimum is obtained as 17.8 mm. So Ex minimum is greater than 20 mm, and Ey minimum is obtained as less than 20 mm. If it is obtained as less than 20 mm, we will consider a minimum eccentricity of 20 mm. So finally, the Ex minimum is 21.13 and Ey minimum is taken as 20 mm. So corresponding this eccentricity will be obtaining a moment. So that is calculated as Mux minimum and Muy minimum. So Mux minimum will be equal to Pu into Ex minimum, and Muy minimum is equal to Pu into Ey minimum, which is obtained as 16.9 kilonewton meter and 16 kilonewton meter respectively. Here Ey minimum is taken as 20. Even though it is by calculation it is obtained as less than 20, we need to consider at least 20 mm. So these are the values obtained for Mux minimum and Muy minimum. So we have calculated the internal moment or initial moment due to the eccentricity of the axial load. So next step is design for bending about x-axis. So we need to, since it is rectangular section, we have calculated the slenderness in both x and y direction. So we need to design, or we need to separately consider the design for both x and y axis. So our first step is design for bending about x axis. So from the calculation of slenderness ratio, we understood that the column is short for bending about x-axis. So we need to design it as similar to a short column subjected to uniaxial bending. Okay. So the column is designed for 80 kilonewton meter and MUX minimum, whichever is larger. As we told earlier, the column is subjected to external load MUX1 and MUX2, which are 40 and 80. So whichever is the larger value we will consider for the design. Okay. So among these two values at the two ends of the column, 40 and 80 is acting. Among this, 80 kilonewton meter is the maximum value. So I am going to consider this for the design. So 80 kilonewton meter is taken. 80 kilonewton meter is taken. And comparing this external moment with the internal moment due to eccentricity. So I am going to compare this external moment 80 kilonewton meter and mu x minimum. So whichever is larger value, I am considering that value for the further design procedure. So while considering these two values, 80 kilonewton meter and 16.9, 80 is the maximum value. So I will consider 80 kilonewton meter for the further design. Okay. So our design procedure is similar to the design of short column subjected to uniaxial moment. We will be choosing a design chart from SP16 based on d dash by d value and fy value, and whether it is circular or rectangular. Based on that, we will choose the design chart from the SP16. And while using the design chart, we need to know PU by FCK BD and MU by FCK BD square. After calculating these two values, I will be choosing the correct or P by FCK value. From that, I will be choosing the percentage of, I will be calculating the percentage of steel. So our procedure is, I have calculated d dash by d, which is d dash is the effective cover and d is the depth of the column. So I have obtained the value as 0.15. And so for a rectangular section with the d dash by d equal to 0.15 and fy equal to 4 and 5, I will be choosing chart number 33 of SP60. And to use the chart, I have calculated PU by FCK BD and MU by FCK BD square. The values are obtained as 0.33 and 0.0833 respectively. By using the chart 33, I've got P by FCK as 0.045, where P is the percentage of steel. From this, I have calculated percentage of steel, which is equal to 100 AS by BD equal to 0.9 percentage. And from that, I got area of steel as 1080 mm square. And I'm going to provide 6 numbers. So while calculating the number of bars required, if I'm choosing a 16 mm diameter bar, the number of bars required to get 1080 mm square will be around 5 point something. So rounding off, I'm providing 6 numbers of 16 mm diameter bars. So again recalculating what is the actual P provided. So required is only 0.9. By rounding off the number 5.2, 5 point something to 6, a whole number. This actually provided percentage of steel becomes 1% and P by FCK becomes 0.05. This is needed for further design procedure. So this is the design based on x-axis. About the x-axis, the column is acting as short. So the design procedure will be similar to a short column subjected to uniaxial bending. And through the design, I have obtained that I need to provide, to resist that this external PU and MU, I need to provide 6 numbers of 16 mm diameter bars. Next step is, I am going to check whether this design is safe while considering the slenderness about y-axis. In the initial step, we have calculated the slenderness ratio and we obtained that the column is slender about y-axis alone. So next I need to check whether this obtained design is safe for slenderness about while considering the slenderness about y-axis. For that, so we know if the column is slender, we need to calculate both MUI and MA, that additional moment which may cause due to P delta effect. So MUI, which I have already calculated, this is the MUI value which is due to the internal eccentricity, minimum eccentricity. This is obtained as 16 kilonewton meter. So next I am going to calculate the additional moment. So our total moment will be equal to MUI plus MAY. This MAY is the total additional moment which is due to the P delta effect. As we discussed in the previous problem, this MAY is obtained from this equation which is given in IS 456. So this equation is MAY is equal to PUB by 2000 into LEY by B whole square into KAY, where PU is the axial load, B is the dimension breadth of the column, LEY is the effective length in about y axis, B is again breadth, KAY is the reduction factor. KAY is obtained from the equation PUZ minus PU by PUZ minus PB, and from as per IS 456 2000 close 39.6 page number 71, we will obtain the equation for PUZ. PUZ is equal to 0.45 FCK EC plus 0.75 FY ASC. Please refer the handwritten note for the substitution. And the final answer obtained for PUZ is 1444.62 kilonewton. And next is we need to calculate PB. So in the equation for reduction factor, PUZ is obtained from this equation. PU is the axial load, PB is the axial load corresponding to the balanced failure, which I have explained in the previous question. So next I need to calculate PB. So the equation for PB is obtained from SP16 table 60 page number 171, and equation is K1 plus K2 into P by FCK into FCK B into D. K1 and K2 are selected based on D dash by D and Fy. So K1 is obtained as point which is given in page number 171 of SP16. So K1 is obtained as 0.184 and K2 is obtained as minus 0.022. This minuses need to be considered. And by substituting these two values in this equation, we'll obtain PB, that is the axial load corresponding to balanced failure as 438.96 kilonewton. And again by substituting the value of PB, PU and PUZ in equation for reduction factor, we'll obtain the reduction factor as 0.641. And finally, we are calculating the additional moment about additional moment about y, that is MAY. By substituting the values in this equation, we will obtain the value as value of the moment as 18.89 kilonewton meter. And finally, we are calculating the total moment about y-axis, which is equal to MUI plus MAY. MUI is about 16 kilonewton meter and MAY is 18.89, and the total will be 34.89 kilonewton meter. Okay, so this is the total moment acting about y-axis. So we are going to check whether the already available design based on x-axis is safe for to take up this moment. Okay, so to check that, I'm going to use SP16 chart number 34. This chart is changed because now the d dash by d value have been changed. Here D represents D dash by D. D represents the dimension which is perpendicular to y-axis, because now we are doing the design about y-axis. So here this D dash by D will be equal to D dash by B. Okay, D dash by B, which becomes B is the dimension which is perpendicular to the y-axis, so which is equal to 0.2. So for a value D dash by D equal to 0.2, Fy is equal to 415, and a rectangular section, the chart is chart number 34. And for D dash by D equal to 0.2, Pu by FCK BD equal to 0.33, and P by FCK equal to 0.05, the value obtained for Mu by FCK BD square from chart 34 is 0.085. From that I am calculating Mu which is equal to, that is multiplying 0.085 with FCK BD square. I have obtained Mu is 61.2 kilonewton meter, which is greater than 34.89, that is 34.89 is the maximum or total moment acting above this YY axis. And for we have provided 6 numbers of 16 mm diameter bar. That design, that's 6 numbers of 16 mm diameter bar is sufficient to take up a load up to or take up a moment up to 61.2 kilonewton meter, which is greater than the total moment acting above Y axis. Hence, the design is safe. So this is an example for how to design a slender column for a given axial load and moment. The first question were about how to check the adequacy of a given design or given value of given dimension of the column and reinforcement. And the second question is describing how to design the slender column. Hope you all understood this. So, thank you.